Hello everyone, this is the 6th week class. Today we are going to study a technique called multiple regression. Right? So last week we studied simple regression, right? Basically, simple regression is used when we have only one independent variable, right? On the other hand, multiple regression is used when we have two or more independent variables. Okay, so just like the simple regression, we want to find the equation which represents the relationship between independent variables and the dependent variable, right? So just like if we have two independent variables, we want to find the equation like this. Right? So basically, we wanna find the beta 0 and beta 1 and beta 2, right? Beta 1, beta 2 are simply the coefficients for the independent variables, right? Now, if we have two or more independent variables, it's very hard to imagine the locations of the points because it is located in a space, right? So for example, if we have two independent variables, let's look at the graph here. So we have x1 here and x2 here and y is here, right? This is three-dimensional, right? So it's kind of a space. If we have a data on independent variables and the dependent variable, right? The point exists somewhere in the space, right? So it's very hard to imagine. So for example, if we have a data like this, right? Let's look at the this data. So y value is 12.4 and x2 is 18, x1 is 28, right? So in this case, if you look at the graph, so x1 is 28 and x2 is 18 and the dependent variable is 12.4, right? So in this case, this point is located somewhere in the space, right? In case of multiple regression, uh, finding the relationship between independent variables and then dependent variable is to find a plane in this case, not the line, right? Because it's a three-dimensional, so we want to find a plane which goes through the data points, right? And the basic idea of finding the best plane is just like the simple regression case. We want to find the plane which minimize sum of distance squares from each data point to the plane, right? It's very hard to draw a graph, but the basic idea is the same. The least square method. So least square method is used to find the plane which best represent the relationship between independent variables and the dependent variable, right? Now, instead of going through, the complicated computation, we are going to use SPSS to get the computer output, and then we are going to focus on the interpreting the results, right? Now let's go to SPSS. So let me show you how to get the computer output for multiple regression, right? So we have here the dependent variable and the independent variables, right? In this case, we have a two. So you go to the analysis and you go to the regression. Okay. Now you choose a linear, right? So you're going to select this one. And you move dependent variable to the right here. And independent variable to the right. Right? And you can, get all the, necessary statistics by using these options, right? But let's directly go to the results here. So you get the three tables here, right? So one table is about the R square, and another one is the ANOVA table, and the last one is coefficient table, right? So we'll talk about these ones today, right? Okay, let me show you this one again once more. So you go to the analysis and you go to the regression and you select a linear, right? And you move variables to the right, right? And if you want to get the, you can get all kinds of statistics here, right? But in our case, these are not necessary, right? So you continue this one and you get the output, right? Okay, let's go back to PowerPoints and then let's try to interpret the results, right? So we are back to our PowerPoints. These are the computer output. This output is slightly different from what we saw in SPSS, right? This one comes from Minitab, right? Minitab is another statistical package, right? Minitab is used in many companies, right? But at the universities we use SPSS, right? So even though this one has the same numbers, but let's try to use the SPSS output, right? So this is the SPSS output. So the first table shows R square, right? R square is in this case 0.974, right? This means what? If you have data on axis, right? X1 and X2, then you can predict 97.4% of Y, right? So it's pretty good, right? The maximum value is 1, right? R is simply the square root of this, right? And let's talk about the adjusted R square, right? This one. Even though we don't use this one very often. But anyway, the reason that we use adjusted R square is that in multiple regression, right? If you add independent variables, then R square goes up automatically, even if the added independent variable is not related to a dependent variable, right? So, you have to reduce the effect of adding, not meaningful independent variables, right? But, think about our case, right? When you make a model, right? So you want to put the independent variables which are related to the dependent variable, right? you don't want to include independent variable which is not related to the dependent variable, right? So you don't need to worry about too much about the adjusted R square, right? Just simply look at the R square, right? So I'm not going to emphasize these things, okay? As I said, if you include the independent variables which are related to the dependent variable, you don't need to worry about adjusted R square, right? Now, this R square comes from, these numbers, right? This one divided by this, right? You get the 0.974, right? So 24.875 divided by 25.549, right? This ANOVA table is the same as the ANOVA table we saw in the simple regression, right? So this one is use the overall model fit. Overall model fit, right? So you wanna check whether your model is good or not, right? So this one is called the total variation, right? And this one is explained variation by the independent variables, right? This one is unexplained variation, right? Just like in the simple regression, right? So R square is computed by you divide your explained variation by total variation, right? So you get the R square. Now let's talk about the hypothesis that we use for this ANOVA table, right? The hypothesis model is not good. Okay, and alternative hypothesis is model is good. Okay, so in this case, this is p-value, right? So this is p. P is less than alpha, right? Suppose alpha is 0.05, right? So you reject the hypothesis. Okay. Now, what is this one? Model is not good. What's that mean? This one means if we use parameters or coefficients, right? In this case, since we have two independent variables, right? So the true regression line, no, I mean the equation is like this. Right? Since we have two independent variables, model is not good means beta 1 and beta 2 is equal to 0, right? All the coefficients are equal to 0, right? That is, model is not good, right? Now, model is good means, in this case, at least 1 is not equal to 0, okay? At least one of the coefficients is not equal to 0, right? So that's this, right? Now, how do we get the p-value here? So this F statistic is test. This one is called the test statistic, right? This one comes from this one divided by this, right? This one is explained variance, and this one is unexplained variance, right? Variance of variance is F distributed, right? And this one comes from dividing this one by this, right? And this one comes from dividing this by this, right? And the p-value comes from the graph like this, right? Remember the F graph, right? F looks like this, right? And this one, so you mark here 92.303, right? The computer computes this area, right? This is p-value. In this case, p-value is almost zero, right? Here, okay? Now, let me repeat this one. So the ANOVA table is used to test whether your model is good or not, right? In this case, the null hypothesis is that all the coefficients are equal to zero, right? Think about this, if these ones, right, are all equal to zero, what does that mean? There is no relationship between independent variables and dependent variable, right? So there is no need to use independent variables to predict y, right? So the hypothesis is that all the coefficients are equal to zero, right? And the alternative hypothesis is that at least one is not equal to zero, right? Now let's look at the coefficients here, right? This one is unstandardized coefficients. This one is called standardized coefficients, right? I'll talk about this one later. And the regression equation comes from this, right? So your regression equation should look like this, right? So 13.109 minus 0.09x1 plus 0.082x2, right? And you see here the coefficient is negative, right? In this case, this one is positive, right? So that means what? There is a negative relationship between x1 and y, right? And then there is a positive relationship between x2 and y, right? Now, before we go into this, we need to check whether, these coefficients are significant. If you look at the p-values, right, we have three p-values here. This one and this one and this one, right? Let's look at the one by one, right? So let's look at this p-value, right? So what is the hypothesis in this case? In this case, hypothesis is this. Beta 0 is equal to 0, right? Null hypothesis is beta 0 is equal to 0, right? And the alternative hypothesis, beta 0 is not equal to 0, right? Remember that the beta 0 is the intercept here, right? So for this hypothesis, right? So p-value is almost 0, right? So in this case, right? So you reject null hypothesis, right? Reject this. That means what? Your intercept constant is significant, right? Now let's look at the this one. 0.001. This one is for the coefficient for the x1 independent variable, right? So in this case, the null hypothesis is beta 1 is equal to 0. Beta 1 is not equal to 0. Okay? So in this case, p-value is alpha, right? So you reject the hypothesis, right? So that means what? Beta 1 is not equal to 0, right? So that means beta 1 is significant, right? Now, so this one is not equal to 0, right? So you can safely say that there is a negative relationship between x1 and y, right? Now, what about this one? Right? So in this case, the null hypothesis is about the coefficients of the x2 independent variable, right? So beta 2 is equal to 0. Beta 2 is not equal to 0, right? In this case, p-value is less than alpha, right? So you reject the hypothesis, right? That means beta 2 is significant, right? So in this case, you can safely say that there is a positive relationship between x2 and y, right? Now let's talk about the standardized coefficients, right? This one, to get this one, right? First thing you need to do is you standardize all the data, right? Let's go to the data, right? So we have the data like this, right? So in order to get the standardized coefficients, right? You need to transform these data to the standardized data, right? Standardized means what? Basically, you use this one, right? So in this case, since mu is the simply the mean, right? So you get the mean of this, right? So you compute the mean, and also you need to compute the mean here. And you need to do the mean, right? And this is the standard deviation, right? Also, you need to compute standard deviation, right? SD, 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 right? And then you compute each one, 28 minus mean, and divide by standard deviation, right? And also you need to compute the standardized number for each of this data, right? Using this equation. Same for this, right? This one is 18 minus mean and divide by standard deviation, right? Same thing for the dependent variable, right? Once you get the standardized data, you do the regression, right? Then you will get the standardized coefficient, right? Okay, this one is computed by using the standardized data, right? Now, what is these ones, right? These are the basically standardized coefficients, right? This is useful to find the strengths of the relationship between independent variables and the dependent variable, right? In this case, if you take the absolute value, right? This one is absolute value is 0.667 and this one is 0.391, right? So you can say that x1 has a stronger relationship with the dependent variable, right? So by comparing, these standardized coefficients, you can check the strengths of the relationship, right? Now let's talk about the case where we have categorical data for the independent variables, right? So far we have seen the cases where we have all the data are quantitative, right? If you have qualitative data, I mean the categorical data, then you need to do something about that variable, right? Let's look at an example here. Suppose you have a dependent variable here, and we have two independent variables. One is for the number of households, and the other one is for the location, right? So in this case, this one is quantitative variable, and this one is also quantitative variable. But location is what? This one is qualitative variable, right? So if you want to do the regression, right, you have to change this data to some number, right? So you need to create a new variable, right? The new variable is called the dummy variable, right? So, for example, if you have a gender, male or female, so you have to transform that data to some number, right? So, usually you use a 1 or 0, right? So if you want to change gender to the number, you usually use 1 for male, 0 for female, right? Now, if you have, in this case, street or mall, right? So you have two categories, right? In that case, you only need one dummy variable, right? Here. So you use, in this case, you use a 0 for street and 1 for mall, right? If you have three categories, for example, if you have three categories here, then you need to use two dummy variables, right? For example, in this case, dummy 1 and the dummy 2, okay? For street, you can use 1 for dummy 1 and 0 for dummy 2, like this, okay? And for the mall, you can use 0 for dummy 1 and 1 for dummy 2, okay? Like this, for mall. And for the downtown, in this case, you use zeros for dummy 1 and 0 for dummy 2, right? Like this, right? So it turns out that the number of dummies that you need is equal to number of categories minus 1, right? Two categories, then you need one dummy, right? Dummy categories. If you have three categories, you need two dummy variables. If you have four categories, you need three dummy variables. Okay. Now let's do an example here. Suppose you want to transform blood type to the dummy variables, right? So in that case, you have four blood types, right? So you have A, B, O, A, B, right? So you have 4 categories, right? In that case, you need 3 dummy variables. 3 dummy variables, right? So dummy 1 and dummy 2 and dummy 3, right? So for the blood type A, you can use 1, 0, 0, right? For these 3 dummy variables. And for the blood type B, you use 0, 1, 0, right? Blood type O, you can use 0, 0, 1. And blood type AB, and you use zeros for all dummies, right? So you change, these ones to the dummy variables, right? So let's try to use, these dummy variables and to get the regression output, and then let's try to understand the outputs, right? So we are going to use, this data, and then I'm going to show you how to interpret the results, right? Let's go to the SPSS. So we are back to SPSS. So we have a data here, sales and the number of households. And I created 2 dummies, right? And here, so I use 1 for dummy 1, 0 for dummy 2 for street, right? And 0, 1 for the mall, and 0, 0 for the downtown, right? So you need to you need to transform the categorical data to the quantitative data, right? By using these dummies, right? So let's do the regression here. So you go to the analysis, and you go to the regression, and you select linear, and you move cells to the dependent variable, and households to independent variable, and dummy 1 to independent variable, and dummy 2 to independent variable, right? And then you get the results, okay? So you will get the results like this, okay? So you have R square table and ANOVA table. Also you get the coefficient table, right? I'm going to show you how to interpret these results by using this output, okay? Now let's go back to PowerPoint. So these are the computer outputs. As usual, we have R square table here, right? So R square is 0.987, right? Pretty high. Now, as I said, the ANOVA table is used to test whether your model is good or not, right? So in this case, the p-value is 0.000, almost 0, right? So you reject null hypothesis, right? So in this case, the null hypothesis is what? Your model is not good, right? So by rejecting null hypothesis means that your model is good, right? Now let's look at the coefficient table. This one is the main thing that you need to understand here, right? So we have 2 dummies, right? So basically your regression equation looks like this. Y is equal to, so let me write here, y is equal to 21.841, right? Plus 0.869x right? And let's use x1. And minus 6.864 dummy 1 and plus 21.510 dummy 2, right? From this, right, you need to create a regression equation for each category, right? For example, for street case, right? Remember that for street, I used 1 for dummy 1 and 0 for dummy 2, right? So you plug in those numbers, 1 for dummy 1 and 0 for dummy 2, you get the y is equal to 21.841 plus 0.869x1, right? Minus 6.864, right? Right? That's for the street, right? And for the mall, we use 0 for dummy 1 and 1 for dummy 2, right? So for mall, we will have regression equation like this. Right? Plus 21.510. Right? And for the downtown, right? Downtown, you get the zeros for the dummy 1 and dummy 2, right? So you get 21.841 plus 0.869x1, right? And then you compare, these things, right? So if you look at the equations, right? Downtown, let's compare downtown to mall, right? If you look at these two equations, in case of mall, the sales is on average 21.51 higher than downtown, right? So by comparing, these equations, right? You can see the on average, which one has bigger sales, right? So let's compare street and then downtown, right? This one is street and the downtown here. So if you look at the regression equations here, you see downtown has a higher sales, right? On average, how much? On average, 6.864, right? So in terms of sales, mall has the highest sales, right? And then downtown and street, right? And in terms of the hypothesis testing for the households, right? Since p value is almost 0, so you reject null hypothesis, right? So that means the coefficient is significant, right? For the dummies, you don't use usual hypothesis testing for dummies, right? So forget about the hypothesis testing for these dummies, right? Just try to understand the magnitude of difference among the categories, right? In this case, in terms of sales, right? Now let's talk about the multi-collinearity problem. When you do the multiple regression, you need to always check whether your model has this problem, right? This problem occurs when you have two independent variables are correlated with each other, right? So why is the problem? If there is a multi-collinearity problem, then strange thing can happen, right? Sometimes you expect positive relationship between a specific independent variable with the dependent variable if multi-collinearity problem exists, this can be negative in regression equation, right? And also sometimes you see that that there is a relationship between a specific independent variable and dependent variable. So there is a significant relationship. But if there exists the multi-coordinarity problem, then in a multiple regression equation, it's sometimes the independent variable turns out to be not significant, right? This type of thing can happen, right? So you always need to check whether your model has, this problem, right? So I'm going to show you how to check this thing, right? If, in effect, there exists multi-coordinarity problem because, two independent variables are correlated with each other, then you should consider dropping one of the independent variables, right? So in order to check whether you have multi-coordinarity problem, you need to check the VIF value, right? So if VIF is greater than 10, then you can say that there exists a multi-coordinarity problem, right? If you have VIF values which are greater than 10, then you expect that severe correlation problem among the independent variables. And then you need to do the correlation analysis among the independent variables. And you need to check, which ones are correlated with each other. Then you need to consider dropping one of those independent variables, right? So that's it. That's the how to handle the multi-coordinarity problem, right? Let me quickly show you how to get the VIF values. Let's go to the analysis and regression and linear. Let's use this one. You move to So you move dependent variable to the right. And you move to the independent variables. And you check this one, statistics. And you click this one. This is a multi-coordinarity, right? Check, right? And you click this one. And you get the results here. You see here the VIF here, VIF. So in this case, VIF value is less than 10, right? So it's okay, right? Now, once you see the VIF values which is greater than 10, you need to do the correlation analysis among the independent variables. So you go to the analysis and you check this one. So, and let's see here. So let's try to get the correlation coefficient among these two. You see here, so this is correlation coefficient. If this one is very high, right? Let's say 0.9 or something, then there is just a very high correlation among these two independent variables, and then you should consider dropping one of them, right? So this is how to do the correlation analysis, right? Let me show you again. So you go to the analysis. This is correlation analysis, and you select this one, and you move, the variables that you want to know whether they have a high correlations, right? Then you move those variables to the right, right? And then you click enter, and then you'll have the correlation coefficients, right? All right, that's it. Let's stop for today. Next time we are going to study a technique called logistic regression, and also we are going to look at comparing the different models, right? In terms of which one is better, right?